Today I will talk about something which is a bit more exotic, maybe for you, but there are growing amount of works on cosmic rays and associated with interstellar dynamics. I didn't make any statistic, but the number of papers is growing. So here you have my email address if you have some complementary questions. So let's move to the lecture plans. There is a lot of stuff I likely do not have time to cover all. There is also a couple of backup slides if you have some more questions. I will go mostly after some introduction, let's say to go into, let's say, some kind of cosmic ray physics. I mean, microphysics. I mean, the way cosmic rays are accelerated, the way cosmic rays are transported into the interstellar medium, because transport is a key ingredient if you want to evaluate the impact of cosmic ray over star formation. Then I will move to astrophysics, and then you will have a break here, showing you kind of complementary stuff that Stephanie just did, is about cosmic ray feedback over star formation, let's say large scales. And then we will move to small scales, and these stuff are, let's say, a bit more speculative until now, but there is some work associated with cosmic ray ionization of molecular clouds. And then we will move to young stars, and we'll show you that maybe these young stars are also interesting to accelerate particles and inject non-thermal particles at very small scale in the interstellar medium. Okay, so just here it's a slide just to show you, to warn you. Of course, I'm in CGS as in astrophysics as usual, and there is a couple of references you may look for if in order to complement this lecture. Let's move to introduction. So cosmic rays. What are cosmic rays? Cosmic rays are non-thermal particles with energy, let's say, ranging at least a few MeV. This is the picture we've got now from some years ago from the Voyager probes, because they are in the, let's say, not exactly in the interstellar medium, but not far from, and they are able to measure the particle distribution beyond the solar modulation. Okay, so down to very rather small energies, kinetic energy, about down to 3 MeV. That is for proton or helium, and a bit larger for electrons. So here is a proton, helium, and electron spectra. Otherwise, the cosmic ray spectrum can last for decades of energy and flux. And this is a kind of very spectacular feature of in the nature. They have a huge power law, decreasing mostly in e to the 3. And then you have mainly two parts above, let's say, 10 GeV. Below this, you have the solar modulation. And above this, you have cosmic rays, which are mostly coming from our galaxy, up to some, let's say, what we call, people do see a leg here. So you have a knee, and then here you have the ankle of the very high energy. And let's say about of order of 10 to the 8 GeV, that mean around 10 to the 17 electron volt. Particles are mostly confined in our galaxy, so they are coming from our galaxy. And then the popping up, there is another component at very high energy, which is likely coming from, which is likely of extragalactic origin, because these particles have so much energy that cannot be confined in our galaxies. They are coming from another source of several sources outside our galaxy. until the end of the spectrum, which is around, let's say, a few times 10 to the EV electron volt, a fraction of zeta electron volt. 1 zeta electron volt is 10 to the 21. That means that here you have almost as the kinetic energy of in one particle is equivalent to what is the energy you have in a ball served by a tennis professional. So here it's a very huge quantity of energy, but you have very few particles, 1 per square kilometer per century. So of course we have some flux because we have large observatories of 3,000 kilometers square to have enough statistics. Okay, an important point is that cosmic rays are mildly relativistic to relativistic, and so they are relatively no number in density, like about 10 to minus 10. So that's ridiculous. But they carry a lot of momenta and energy. So if you make the products of the density times their temperature, it can be equivalent to the thermal gas because the temperature is high because it's non-thermal, okay? So they have as much as energy as the thermal gas. So they are in equipartition on average in our galaxy. So the amount of information we have on cosmic rays is thanks to especially to the AMS experiment, which is on the ISS, and which is measuring the different species you have in the cosmic ray spectrum. And especially it's, of course, proton and helium, but also heavier elements like lithium, boron, beryllium. And these ones are interesting because they are very rare in the nature. They are mostly exclusively produced by cosmic rays through with what we call spallation reactions. That means cosmic rays, C and O nuclei, which are hitting the interstellar medium and producing secondary elements, a bit lighter. And this is a large amount of information we have on the cosmic ray propagation in our galaxy from these measurements. This ratio is very important for primary to secondary to primary, for instance, boron over carbon. It's a good wealth of information for the way the cosmic rays are propagating in our galaxy. I will come back on that later. So why cosmic rays are interesting for ISM dynamics? There are, let's say, at least 3 points, maybe more. First one is that is just mostly because of pressure effects. Cosmic ray can carry a lot of pressure, and especially here, the pressure of cosmic rays is hidden in the total pressure of gas magnetic field, and is here, in fact. And here you have a gradient of the pressure. The gradient of pressure is a force. And if you have a huge gradient of cosmic ray, you can have a huge force acting on the dynamics of your modifying the, say, the speed of the fluid. And this is in that way that cosmic ray can have some effect over the main instabilities. You have macro instabilities in the ISM, important in the ISM dynamics. I mean, Kelvin-Helmholtz, radiated error, magnetorotational, Parker-Jeans, thermal, even Fire-Rose Myro. So in my backup slides, I have a couple of references which address this problem for each type of instability if you are interested in. But on top of that, cosmic ray, because they carry a lot of pressure, can create their own instability. We come back on that. This is a streaming instability. This is a very important instability linked to cosmic rays. They can also produce some other type of instability because they can carry a lot of current. So for the G cross B force, they can create, in fact, magnetic field. Another aspect is ionization and gas heating. So these address mostly low energy cosmic rays because the cross-section has a peak for ionization, has a peak for around MeV for protons, or let's say a few hundreds of electron volt for electrons. And cosmic rays are interesting for ionization because they can penetrate at high Coulomb density where the radiation cannot go. And in that case, it can produce some minimum level of ionization at high colon density, and then help to couple magnetic field and gas. There are also, each time you have ionization, you have some heating process. So these are a strong source of heating. Here is, let's say, the average heat input per ionization as function of the hydrogen density in different medium. You see, from diffusive cloud to disk, here is for atomic gas. So each time they can contribute to heat the medium. So I will treat also this aspect in the second part of my lecture. One aspect I will not treat at all is the impact of dust. There is also a growing amount of work, both on theoretical part and both also on experiment, which you have some dust particles which are with a flow of energetic particles, which you can term as cosmic rays. So cosmic rays are important for the charging and heating of the dust. So here you can see this reference. This is important because, in fact, they are especially important for dust charging, and because the cosmic ray can induce a cascade of secondary particles, and especially UV photons, so deep at high colon density, which can affect the dust coagulation and so mediate the medium resistivity. So this is likely an important process. But as I'm not a specialist of this stuff, I will not talk about. There is only a backup slide, so I would suggest that for the next school year, you can have a lecture on cosmic rays and dust. I think it could be interesting. So, okay, so coming back to the dominant source of energy in the interstellar medium, as Stephanie Walsh just said, you have different ways to steer the turbulence. And so you have many different instabilities which are linked to gravitation, rotation, or magnetic field. You have processes linked, of course, with massive star activity, winds, radiation, or H2 region explosion, and finally supernova explosion and jets finally. So if you evaluate let's say, the amount of energy input by all these processes, on average, what you find which is dominating is supernova explosion. And supernova are intimately linked to cosmic rays, as I will show you, because they are likely the main sources of cosmic rays. So let's move to supernova energy input. So you can calculate it by considering the typical mechanical energy deposited during a supernova explosion, so around 10 to the 51 air per second. The efficiency in converting the energy transfer to ISM gas, which is, you have some uncertainty of that, but let's say 10%. The supernova rate, which is about, let's say you have about 3 supernova per century in our galaxy, and the volume of the galaxy. So you end up with this number, which we will use hereafter to evaluate what fraction of this energy is imparted into cosmic ray. And the calculation is as follows. So from the secondary to primary ratio I show you about cosmic ray previously, you can deduce typical residence time scale of GeV cosmic rays in our galaxy, which is about, let's say, about 15 megayears. And from that, you can evaluate the energy density you have in your cosmic rays. And what we found is about, if we assume that 10% of a supernova mechanical energy is going into cosmic ray, you end up with something about 1 electron volt per cubic centimeter, which is more or less the energy you have in your gas and magnetic. So cosmic rays are roughly in equipartition with magnetic field and gas in the ISM. So you can convert it into a luminosity, total luminosity in your cosmic rays, which is about 10 to the 41 arc per second. So you need to have some sources which are efficient enough to replenish this type of luminosity in our galaxy in these non-thermal particles. It's this one? Yeah, this for a model of acceleration. We come back on that. There is a bit of uncertainty, always a factor 2 in astrophysics, you know. Okay. So just one note here. I will always talk about cosmic rays. So exactly for me, what cosmic rays are is the particle we observe, okay? That does not mean that you have sources in our galaxy which are producing non-thermal particles, which are all contributing to the cosmic ray spectrum we are observing now. Some source can produce non-thermal particle, but these non-thermal particle may not be contributing to the cosmic ray spectrum. That's kind of, let's say, kind of definition. What are the sources? You have plenty of sources of potential cosmic rays in our galaxy. So I told you that supernova and especially supernova remnants are the main one. This is, let's say, the kind of standard model in cosmic ray physics. They are accelerating about, or let's say, up to 0.1 to 10 peta-electron volts, so 10 to the 15 electron volts, the so-called the knee I just showed you before. So even to accelerate particle at such high energy, it's really challenging. It's not an easy task. Some other source may be massive star clusters. So they are kind of renewal of, let's say, massive stars. This is a long, a very old model, let's say, but they are kind of renewal of massive star cluster thanks to gamma ray observation. I will show you. So in a bold, these are the sources I will discuss in this lecture. I will not talk too much about pulsars, which are thought to mostly inject electrons and positrons. So different kind of, let's say, cosmic rays, which are dominated by protons, compact sources, and then I will discuss a bit about young stellar object, which is a bit more speculative, but there is more observation showing that at least in jets, young stellar objects have a non-thermal radiation synchrotron. So there are here some at least relativistic electron. Okay, typical scale of these different objects. Massive star cluster have through, if they produce super bubbles, they can have inject cosmic rays over a scale, let's say, about the galactic disk height, 10 to 300 parsec. Supernova remnants, of course, it depends widely on which type of medium they are propagated in, but typically they inject this non-thermal component over a scale of 10 to 100 parsec. Then pulsar, through their pulsar wind nebula, it's about 10 parsec, and then compact source 1 parsec, and then young stellar objects is about the jet length, about 1000 AU. And these are interesting because they can re-inject and they kind of feedback at a small scale. Then, so it is a matter of acceleration model to evaluate the luminosity of each type of this source. And this is where this efficiency is coming from. Okay. So now let's move to a bit more physics. Before talking about physics, I will show you some observation, which where we have some clues about the cosmic ray source. So let's start with supernovae remnants. Here you have two examples of and the radio domain. Here is a radio emission, so basically it's synchrotron, okay, by relativistic electron, let's say GeV electrons, producing radiation at the gigahertz in microgauss level of magnetic field. Here is an old supernovae. This phone number, CTB1. Here, where you see you have also some polarization of the magnetic field. You see that the magnetic field is almost aligned with the shock front. And for younger one, this is a SNR 1006. So it explode in 1006. Here you have more radial component of the magnetic field. So the difference is likely associated with some let's say instability occurring in younger objects, for instance, Rayleigh-Taylor, which can elongate the gas and also with it the magnetic field. Now, how this looks at higher energies. So here is a nice picture of the Tychos supernova remnant at X-ray, thanks to the Chandra satellites, and it's a very nice picture. So the interest of Chandra is the instruments have a very high angular resolution, and in fact you can see clearly the ejecta part that was formerly composing the star, different elements, silicium, etc. And for different color at lower energy, and let's say at energy between 4 to 6 keV, you see in blue it's synchrotron radiation. And especially you can see, I will come back on that, very thin filaments which are marking the shock position. So this is evolving with time. There is some movie showing you the expansion of the object. This object also produced gamma rays, and this has been detected from using some instruments which are the Cherenkov telescopes, which are on ground, which detect the showers produced by the gamma rays in our atmosphere. So the shower produce, let's say, blue light, which is collected, and then you can reconstruct the gamma ray direction and energy. This shows, so of course, the problem of gamma ray instruments is very bad with respect to X-ray angular resolution. So you are a bit blurred, but you can also, here is the Chandra image is here on magenta. Okay? So you have some correspondence. And gamma rays are likely produced by inverse Compton emission of the same electrons which are producing this X-ray synchrotron. Or they can also be produced by protons, and this is what we are looking for as a cosmic rays, through the decay of neutral pion. So while proton interact with an interstellar medium material, they can produce some nuclear interaction, and so producing neutral or charged pion, and the neutral pion decay into gamma rays, which can be this signature. But for now, we still have a kind of degeneracy among the two. We are not sure where the gamma rays are coming from which process. I just want to come back a bit of time on this X-ray image, because it's nice, or also because as you can almost resolve the filament size, you can put some constraint on the magnetic field behind the shock. And this, I thought is a very nice results. Basically, the filament size has to be smaller than the two lengths, which are either the advection scale, that is, particles are advected behind the shock for a synchrotron loss time scale at a speed, so the shock speed divided by the compression ratio. So we are downstream. And the diffusive scale, particle can have some diffusive random walk, but still here you have within a loss time scale. So as the loss time scale depends on the magnetic field, you can put some constraint on the magnetic field. And what we find from the size of the filament is that the magnetic field here is produced by TeV electrons with a magnetic field strength about 4 to 5 100 microgauss. That is 2 orders of magnitude what we have usually in the interstellar medium. So something is going on here, and is likely connected with the acceleration of cosmic rays themselves, producing the self-generated turbulence I will talk about. Few words about other source, massive star clusters. There are a growing number of massive star clusters observed at gamma rays. Here is an example of a very nice, very rich region about the Sinus X region. Is you can see you have plenty, especially you have Sinus OB2, which is a very active massive star cluster. The gamma rays show very hard spectrum here, about E-2. So there is let's say a source of freshly accelerated cosmic rays there, up to, let's say, well, we have about a few tera electron volt. So this confirms there can be a source of cosmic ray either. A word about pulsars, especially the Crab Nebula, because it is very important in high-energy astrophysics. Here you have a multi-wavelength view of the Crab Nebula. So you have a pulsar, you have a very fast wind, I mean, with a Lorentz factor about 10 to the 6. So it's highly relativistic. And then you have a termination shock. And behind this termination shock, you have the nebula. And this is what we see on radio, infrared, visible, HST, ultraviolet, X-rays. Again, here, thanks to Chandra, you have a very nice image. Here you see the pulsar and the wind here. And at gamma rays. And gamma rays is, so you see we have a very nice multi-wavelength spectrum of this object. And this object is very important at gamma rays because it's a kind of standard candle. We compare a gamma ray luminosity to any kind of source at the fraction of the Crab. New stuff recently, which has been observed around some pulsars, like the Geminga, which is about 300,000 years old pulsar, is that you have some very extended gamma ray emission, which we call gamma ray halo. So if you plot the profile of the gamma rays from the nebula, in fact, the nebula is here, okay? As a function of the distance, you have something, a kind of 1/r profile, which can be fit by a diffusive law, and then you can put some constraint on the diffusion coefficient of the particles. And what we find is that at this high energy, this is a result by Hawke, you have a diffusion coefficient which is reduced about 2 or 3 orders magnitude to what we got from the B/C ratio from the, let's say, the standard diffusion coefficient of cosmic ray propagation in our galaxy. So something is going on here connected with the escape of cosmic rays. I will come back on that also later. Cosmic ray escape is really a real problem, which is not solved yet. So the game actually in the high energy community is just for information. It's nothing to do with ISM dynamics, let's say, is to find some pivatrons. So the extreme objects accelerating cosmic ray up to the 10 to the 15 electron volt. And we have recently in China, the LASSO observatory, which is on ground. So which now has released its first catalog. And in fact, what they found several sources which are associated with TeV cosmic rays, so let's say 100 tera electron volt gamma rays. But there is no clear counterpart yet identified because of the weak angular resolution. But so this work is ongoing, and in fact is triggering a lot of activity in our community. This was just to inform you. Moving back, maybe so for objects you are more interested in, here are young stellar objects, and especially their jets. They are usually not known to be strong non-thermal sources. Basically, the radio emission is rather dominated by free emission. But recently, there have been some campaign to observe several jets of this object, and which have uncovered some non-thermal synchrotron emission produced by relativistic electrons. So there is a couple of objects from DJTO, which is let's say solar mass object, to this one HH8081, which is a massive object, and especially here, thanks to the good angular resolution at the VLA, you are able to follow, in fact, the index of the emission along the jet. So from negative to positive, negative synchrotron, positive is free. And you see that it's varying a lot along the jet and is likely associated also with the jet width, and possibly associated with a kind of Rockwell emission shocks you have along the jet, producing some nodes. And as it shocks, you can have particle acceleration, electron acceleration, producing synchrotron radiation. There have been some in this object is producing gamma rays, but the analysis is not so, let's say, that has to be taken with some care. Okay, this kind of summary you can read. I will move on because otherwise we'll never finish my. I have to talk about cosmic ray acceleration mechanism now. How these particles are accelerated. So first of all, one big argument if you want to know what the typical maximum energy one source can produce. So you have one source with some size and magnetic field. And from that, you apply this criterion, which is so-called the ELAS criterion. You set the size of the source to the Larmor radius of the particle. And here is you have the energy. So you can express the magnetic field as a function of the size of the source and for different energy. So you plot the log of the magnetic field on the log of the source, and from different energies of charge, you can see that up for different type of objects, which different size and magnetic field, you can see what is typical, the confinement energy, the maximum energy a particle can reach in that source. This is the ELAS criterion. This is, let's say, a rough criterion to say you that what maximum energy you can expect as a non-thermal particle for a given source. So in order to accelerate the most energetic particles, you need, let's say, a source with which are rather at least minimum extended and for strong magnetic field, because this is a confinement criterion. So the stronger the magnetic field, the more confined the source are in the region. So I will describe now the, let's say, the standard model of cosmic ray acceleration by shocks. This is the so-called diffusive shock acceleration. So this is a theory which going back to the late 70s. There have been a series of work around 77, 78, 80, 81, which all conclude to the same. So here I summarize you. So you have diffusive shock acceleration. So let's take each term and explain them. So shock, you need a thin discontinuity for the thermodynamical quantities as seen by the particles. So the particles which are energetic see the thermal gas as a discontinuity, as a shock. Okay, so you have a sharp discontinuity of the different quantities upstream and downstream. It is diffusive. In that case, you need some turbulence upstream and downstream, before the shock, after the shock. We usually use this picture of racquetball. You take the turbulence as a racket player, and they kick the ball on each side of the shock. And each time the particle crosses the shock, it gains some energy. And if it does up, down, up, which we call a Fermi cycle, it gains a relative amount of energy, which is constant each time. Wow. And this is the amount of energy. But each particle has some probability to escape downstream each time because it can be advected with the flow. And if you convolve this energy gain and the probability to escape, you end up with a particle distribution, which is a power law, which only depends on the shock compression ratio, which is a beautiful result because usually it's rare that you have a theory in astrophysics which depends only on one parameter. And this is the case. And for the strong shock, this compression ratio is 4. And then you expect E-2 spectrum. This would have been nice, but the problem is that cosmic rays, I told you, carry a lot of pressure, and then they can back react over the shock structure. So in fact, cosmic ray acceleration is an intrinsic nonlinear process. And this is why it is still an active research field. So here's the picture. You have in dash blue the unmodified shock here. And then if you add cosmic rays, they modify the inflow. In fact, the fluid will be one that you have cosmic rays at the shock with some pressure. So they will start to back react over the inflow. And then the shock itself is reduced what you call a subshock, which is smaller than the unmodified shock, let's say. It's smaller than 4 for a strong shock. But in total, the cosmic ray pressure enhances the gas compressibility because you modify the adiabatic index. And basically, in total, if you take all compression ratios, the total one, far upstream to far downstream, it is larger than 4. So that explains that low energy particles, which are more or less confined closer to the shock, see a compression ratio smaller than 4. So they have, with respect to the test particle solution, let's say a softer spectrum here. If you put R equal 3, for instance, you will end up something with a bit smoother than E-2. But high energy particle, we see, on contrary, compression ratio, which are larger. So here you have harder spectrum than E-2. So you have a kind of concave spectrum at the shock front. And here is the escape fraction of the particle. Now, in order to answer to your question about the fraction of, let's say, the energy of the kinetic energy of the shock, which is imparted into the particle, it's really a difficult question because it's really microphysics. That means that you have a very refined plasma physics to answer to this question, because you are heating your gas when you have a shock, and then you extract a fraction of this heat gas, and you put it in non-thermal particle. But what fraction you have to use depends on plasma microphysics. And for this, you need to have some numerical simulation. And especially here is an example of hybrid simulation. So electrons are treated as fluid, but protons are following a kinetic simulation. So you solve a kind of a particle in cell approach. Here you have the structure of the shock. So you have an incoming plasma, which is reflected at the shock front, and that gets accelerated. Here is the energy of the particle. So you see that they are cold and then they are heated, and they are so much heated at different positions that they can acquire some non-thermal tail. And in fact, the ratio of this point to the maximum one gives you this injection rate. But you have to really rely on this simulation to evaluate it properly. So what we found is around 10%. But this is strongly dependent on several effects, especially the magnetic field obliquity at the shock front. And so this injection rate can vary a lot, especially due to the magnetic field. Here you have some other simulation. We did some with colleagues, which combine particle in cell for cosmic rays only and MHD-1 fluid. and you don't see well, but you have a 3D simulation. So you have the shock structure, and you see as function of time here, the turbulence which is developed by the cosmic rays themselves. So you have a kind of filaments which are produced ahead the shock and producing magnetic field. And at the end, in fact, you are losing your shock more or less because the turbulence also back react of the shock front. And so it's really getting difficult to see where the shock front is. So this is more or less the state of the art of particle acceleration at shock. Multiple shock can happen in some system, especially in massive star cluster, because you have plenty of winds and the stars are close together. So the winds will interact each other. And each time winds will interact each other, they will produce some shocks. So you can have networks of of shocks, and in that case, the solution is not E-2, but is E-1. It's either harder spectrum of cosmic rays. So this is the takeaway message. Basically, you have a theory which predicts you E-2, P-4 and momentum. Basically, you have some kinetic energy at the shock, which give you about 10% into cosmic rays, and then cosmic rays can produce about this level for magnetic field. You have a ratio of C to the shock speed for the magnetic field. They are able to produce magnetic field, as I show you for the filament of the supernova remnants. And but the problem is that this is intrinsically a non-linear process, which is still under investigation. It's very difficult to. There are other processes to accelerate particles. If I have time, I will talk about it. Or you can talk Stephanie, because she co-signed this paper with Brown Galaxies. Cosmic ray transport theory is in interstellar medium, so I have about 2 minutes to talk about this. So I will take the question now. Right, yes.
Hello, thanks for the interesting talk. So you mentioned earlier about how cosmic rays are able to inject energy and help with heating. So I was just wondering, because earlier we had a talk on feedback. So I was wondering how that compares to, for example, the feedback of stars, and how that would change the dynamic of the molecular clouds around star-forming regions. Or maybe this is something that you will cover, because I think you said.
Yes, I will cover this after. But this is kind of complementary of the first lecture, because with the same tools as presented this morning, especially the B-fluid approach, you can account for cosmic rays and about the effect of star formation rate, which is basically a factor 2. I will show you about. It will reduce by a factor 2 the star formation rate, including cosmic ray. This is a kind of takeaway number, if you want. I will show you.
Yeah, because I thought intuitively, like, it'll probably scale with the radial. I mean, like, as in if it's further away from the central star, then it probably has high impact, because that's lesser radiation from the main star. And then.
So you have to disconnect about the source. You have 3 problems. You have acceleration at the source. You have escape from the source. I will show you. It's not an easy problem. It's not solved yet. And then once they are released, how they can be transported into the interstellar medium. That means that you can have a source which can act over your interstellar medium at some distance for some time, because cosmic ray diffuse.
Okay.
And that's a really tricky part.
Okay, awesome. Thanks.
Other students.
Hi, thank you for the talk. I was wondering if what a contribution may have the starburst galaxies to the extragalactic cosmic rays, if they are, I don't know, important.
To my knowledge, I'm not sure that the main source of extragalactic, so the extreme energy, okay, the main source of, because starburst galaxies are more or less our galaxy, but with more star formation. And we do not expect the maximum energy to be much larger, let's say maybe a bit more, but not much. In order to accelerate 10 to the 20 electron volt particle, it's really challenging. And so you need rather jets, relativistic jets, so AGN jets, active galactic nuclei jets. So strong magnetic field, small scale, but still you can get this Elias criterion 10 to the 20, or very large object like shocks in the galaxy cluster. And these are the two main, let's say, source of high energy cosmic rays with gamma ray burst also.
Thank you. Can I ask another little question? You showed the distribution of the cosmic rays with the knee and the ankle. Why we don't see more energetic cosmic rays? Is something
above 10 to the 20?
Yeah, is something instrumental, or we don't expect
No, it's not instrumental. We are so there's two ways to cut the spectrum. Either the source cannot accelerate beyond some energy, and actually this is more or less the case, or if the cosmic ray source is far away, while a proton, ultra-energetic protons will propagate into the interstellar intergalactic medium. In the frame of the proton, they will see the CMB as gamma rays. So they will have some P gamma interaction, which produce secondary pions either, so they have losses. So you have a kind of horizon of ultra energy sources. This is a so-called Greisen-Zatsekin-Kuzmin effect cutoff. So these are the two processes, but we likely think it's more connected with a maximum energy, intrinsic maximum energy of the source now.
No, I was just wondering, the efficiency, the 10%, how does it change as a function of the shock velocity and the magnetic field? At what point we need to take cosmic ray into account in the energetic balance evolution of a shock?
Okay, so this is still an open question. So with the magnetic field, in fact, there have been a lot of fight. I was among them. About the effect, exact number for the angle. So you have your shock, you have the magnetic field along the shock normal. This is the parallel case. And the magnetic field can be along the shock front. This is a perpendicular case. So what 2D simulation like this one by Damiano, for instance, Caprioli, show that this is for parallel shock, but they show that as you are moving to more obliquity, above 50 degrees, the injection drops. Because the problem is that the particle has to escape upstream in order to start diffusive shock acceleration. And they are linked to the magnetic field. And as the magnetic field is along the shock normal, it gets more and more difficult for a particle to get injected, okay? So, but this angle depends on the galvanic Mach number of the shock. And this is what we found with some colleagues using these techniques. That for very high galvanic Mach number shocks, let's say 100, what you can have for supernova remnant, it can go up to 70 degrees. Now, Damiano Caprioli is coming back with 3D simulation. And he found that for almost perpendicular shocks, you can still inject particles and have diffusive shock acceleration. So you see, it's very sensitive to the number of, if you have 2D or 3D. 3D turbulence is different from 2D turbulence. Like we have some surprise, so it's still ongoing. But let's say up to 50, 60 degrees, you have mostly 10% into the cosmic rays. And it's roughly independent of the shock speed. Takeaway message.
Other questions?
So it's a perfect follow-up to this. Has anyone worked on the situation with no magnetic field?
Pardon me?
With no magnetic field, what happens?
With no magnetic field, I don't know what you mean by no magnetic field, because you are...
First supernova, there is no magnetic field.
Let's say very high galvanic Mach number, more or less, or Yes.
Yeah.
You put a magnetic field to zero.
If you want not zero, like epsilon.
Yeah, yeah.
magnetic field.
But in that case, this is what we found is that you can inject particle up to very high energy because then the particles are less linked to the magnetic field line up
How
the
do
shock.
they get accelerated?
By the same process, by diffusive shock acceleration. The problem with the problem is to start to accelerate them, to extract them from the thermal pool behind a shock. And they have tendency to follow the magnetic field line. So if the magnetic field line is along the shock front, they will follow it.
But if there is zero?
They will not get accelerated.
But if there is zero?
Is there zero magnetic field or turbulence?
No, magnetic field, zero. That's my question.
Yes, if there is zero magnetic field, well, I never thought about this because there is always a minimum. They will start every time. A minimum magnetic field will follow whatever the magnetic field line. Otherwise, they can have ballistic motion and escape at sea. In that case, if you have no magnetic field, of course, the particle is not confined. So you will get no acceleration, of course, in that case.
Any other question before we continue?
Maybe you are going to talk about that later. I was under the impression that there was some kind of tension between the measurement of Voyager and about cosmic rays, let's say ionization rate.
I will talk
And,
about
you will talk.
ionization, you mean?
Yeah, and ionization is.
I will talk about. Don't worry.
No spoilers. Let's continue.
Okay, so the challenge is to finish in 45 minutes. So okay, so let's move to transport. So I've told you about Larmor radii. So the particle, by default, if you have a homogeneous magnetic field, will have a gyro motion. This is the Larmor motion. You probably know that. In fact, cosmic rays they fulfill this type of equation. If you want to know the position and the momentum of a particle along magnetic field, you have to solve this couple equation. Very simple. QE, the electric field, which can accelerate the particle, and V cross B, which is at the origin of the scattering and the diffusion process. In the interstellar medium, both E and B are turbulent. So they will have impulse some random behavior of the pitch, what we call the pitch angle of the particle. That is the angle of the speed of the particle with the magnetic field. I will show you this in a minute. So a particle can go a random walk along the magnetic field or perpendicular to the magnetic field. Move on. So along the magnetic field, because you have some perturbation, the particle, so this is the Larmor radius is perturbed. And in fact, the particle start motion like this, but then can go back because of this scattering. And this is at the origin of the diffusion process along the magnetic field. Also, a particle can jump from magnetic field line to another. This is contributing to the perpendicular diffusion. But what dominates the perpendicular diffusion of particle is mostly the behavior of the magnetic field lines themselves, because magnetic field is turbulent, so you have a magnetic chaos. And if you take a bunch of field lines at one position and then you let them evolve, they will diverge from each other. So if you take a bunch of particles here, they will get dispersed perpendicularly to the magnetic field to this, what we call magnetic field line random walk or magnetic field line wandering process, which is dominating the perpendicular diffusion of cosmic rays. So what we are talking about, so in cosmic ray transport, the scales are very important because you can get completely messed if you do not evaluate the proper scale. When we are talking about cosmic rays which are able to have an effect over the dynamics of the interstellar medium, it is GeV cosmic ray, because these particles carry most of the pressure. You see that the spectrum of cosmic rays is very steep. and is dominated by the relativistic component. So GeV cosmic ray dominates the cosmic ray pressure. But GeV cosmic rays are alarmar radius about, in 1 microgauss, about 5 AU. This is very, 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 very small at the interstellar medium scale. So the tricky part is to have fluctuation at this scale. It's not obvious in the mean interstellar medium. So in that case, you have two types of turbulence. Right? Cosmic ray transport is intimately linked with turbulence. You can either have the turbulence which is injected, let's say, at large scale. With respect to this one, it's not difficult. You take, for instance, supernova release some energy around 10 to 100 parsec. And then it cascaded down to 5 AU, possibly. If you can see that you have the level of turbulence at this very small scale will be small. So the effect about scattering particle will be small also. So at this energy, we mostly more rely on what we call the self-generated turbulence. That is the turbulence triggered by the cosmic rays themselves. I will come back on that. This is a very important process, which is not yet captured by the B-fluid simulation completely, let's say. And so this is, yes, I come back on that. I have to hurry on. So just one number you have to keep in mind is the typical value of the diffusion coefficient you have for cosmic rays in our galaxy, deduced from secondary to primary ratios. So I show you boron over carbon. This is our observation. You see the very nice data. I mean, and you have a and from B over C, in fact, you can deduce using simplified model as diffusion. You can deduce a typical diffusion coefficient for cosmic rays at GeV in your galaxy. You will read it at 1 GeV. It's about 10 to the 28 centimeters square per second. At 1 GeV. Keep this number in mind. This is a reference value for cosmic ray diffusion coefficient in our galaxy. I will skip that. These are the main model of cosmic ray transport. So we are able now to have some microphysical model which can help you to derive some, let's say, theoretical value of this diffusion coefficient once you know the level of turbulence. Here is the turbulence part. Is the delta B is the amount of perturbed magnetic field you have at some scale. K, we use K or 1 over lambda. And yes, delta B square over B square. And you see that the stronger the perturbed magnetic field, the smaller the parallel diffusion is. The smaller the mean free path of the particle along the magnetic field is. So the mean free path is the mean distance between two interactions with magnetic perturbation. The more the turbulent the field is, the smaller it is. The particles are more confined because they are more deflected by the turbulence, okay? Whereas the perpendicular mean free path scale has delta B to the 4 over B to the 4 with respect to the parallel one. So, of course, if you enhance the perturbation, you will disperse more your particle. Okay. So this was more or less a model for cosmic ray in the background or large-scale injected turbulence. But now, cosmic ray, as I told you, can inject their own turbulence. And what here is a picture, let's say. So basically, you have magnetic field, a particle which is moving through the Larmor radius along the magnetic field at C. If you take a lot of particles, I will show you, this is a streaming instability, they can have a tendency to move all together along C. And if they move at speed larger than the Alfvén speed, they will trigger some fluctuation, some turbulence. which are mostly propagating along the magnetic field. This is what we say that they produce slab turbulence. That is, the wave vector of the turbulence is along the magnetic field. Okay, it's 1D turbulence, more or less. And so we are able to, there are some theory, a lot is our books, and to evaluate this. So the parallel mean free path imposed and perpendicular one imposed by this self-generated turbulence. So yes, I would like to take a few minutes on that because this is an important process. This is a streaming, cosmic ray streaming, because it shows you that cosmic rays behave differently as a gas. And it's important to understand that. Okay, so all particles are moving at c along the magnetic field, but they can have a distribution of velocity. The particle can move in that direction or on that one. So if you take a population of cosmic rays, here is an isotropic distribution. So on average, they will move at 0. Okay. But there are always a minimum amount of anisotropy. There are a bit more particles moving forward than backward. For instance, you have a source of cosmic rays. It injects more cosmic ray in that direction. So we have a tendency of anisotropy. This anisotropy will be converted in drift speed, so a common speed of all particles, okay? And if this drift speed is larger, let's say, than the Alfvén speed of your medium, the background plasma does not like this. It will back react in order to, let's say, reduce the anisotropy. So what will happen is that you will produce some waves with momenta, which in the same direction as this, which will take some parallel momenta of cosmic ray away in order to reduce this anisotropy. Okay, you will try to erase this part, producing waves which carry the excess of momenta along the magnetic field. So this is the essence of the streaming instability. And waves mean magnetic fluctuation. So that means that way, cosmic ray can produce their own magnetic field at scale, which is of the order of the Larmor radius of the particle, at very small scale for GeV particles. I hope it's clear. It's an important aspect. If you calculate the growth rate of the waves, in fact, it depends. In fact, it depends on the gradient of the cosmic ray along the magnetic field. So the stronger gradient you have, the shortest the growth time here you have. Okay. And this is likely very important, this streaming instability close to sources, because in cosmic ray sources, I told you that you have more or less equipartition of cosmic rays with gas and magnetic field in the interstellar medium. But in sources, it is not the case. In sources, cosmic ray pressure dominates much over the gas pressure and magnetic pressure. So you have kind of over cosmic ray pressure around source. So you have local source with some high cosmic ray pressure and a interstellar medium with lower cosmic ray pressure. So you have a cosmic ray pressure gradient around source. And then, as I told you, the streaming instability can get triggered around source because of this gradient, the presence of this gradient. And then you can have production of magnetic field around source for some time by the cosmic rays themselves, which have tendency to confine them for some amount of time, which is difficult to calculate. In fact, we have tried to do this. It's also a nonlinear process because you have to couple an equation of kinetic equation for cosmic ray pressure and wave pressure. Here is an example of solution. So you take a supernova remnant, 10 GeV particles, and you have this solid line. The evolution of the cosmic ray pressure as function of time. So this is the time of reference, is the time scale after which half of the cosmic ray pressure in your supernova remnant has escaped. and it is diluted, you see, with time, and you take it takes about around 100,000 kilo years in some medium. Here it's a warm neutral medium, because the amount of waves can be controlled by the damping process, the waves you can have. So in fact, that shows you that the source can confine this cosmic ray for some amount of time. And as you can have a kind of overpressure of cosmic ray around source for this amount of time, this will locally modify ISM dynamics over scale of, let's say, few tens to 100 parsec around sources for some amount of time. So if you want to properly account ISM dynamics, especially in the disk, you have to, at some stage, account for the extended effect of sources in the ISM. Of course, 100 kilo years is more compared to million years, but if you redo the same experiment for MEV particles, you end up with a few million years to escape, particle to escape. And MEV particles are important because they are a main source of ionization. Okay, how much time? 30? Okay. Okay. This was the physical part, let's say, cosmic ray. I thought that you could ask me some question at this stage, but you can ask me after that. I move to the astrophysical part. So the pointer does not work anymore. That's the problem. Don't worry, that's fine. What motivates? Why hell do we need to account for cosmic rays? Let's say, because star formation is already quite complex. So why bother with cosmic rays? So I will try to convince you that you should maybe to take it into account at some stage, let's say. About, let's say, at large scale, you have galactic winds, which are well observed. Here you have two images, one of a galaxy, let's say a bit far away, I think about 15 megaparsec. You cannot see well, but you have outflow from the galaxy. And of course, these outflow are important because they expel gas, which this gas is not available to form stars. So the more the gas you expel, the less star you can form. Okay, this is an important aspect. Here is a picture, a nice picture of a starburst galaxy, M82, which is a spectacular, which has a star formation rate is about 10 times our Milky Way. And this galaxy produces a huge amount of strong winds, and you have 30 supernova per century in this object. And again, with supernova are associated cosmic rays. If you take 10%, you have some amount of cosmic ray expected to be associated with this stellar activity. Another hint is this is a galactic disk as seen by gamma rays. So gamma rays are interesting because they trace gas and cosmic ray. Thank you. That is not the same. Okay, whatever. So in fact, these gamma rays are the convolution of cosmic ray density and gas density. Okay, so once you know the gas density, you can evaluate the cosmic ray density. This is what the trick is done. So most of the cosmic ray sources are in the galactic disk, no surprise. But that means that, as I told you, you can expect to have a kind of overpressure at some state, a lot of injection of cosmic rays, which can have a tendency to move up and to help to expel gas as winds. So if cosmic rays can help to expel gas as wind, they will have an action, direct action of the star formation rate, because they will expel more gas. So people have tried to look at this. I will move directly to simulation. Okay. Because this is connected with Stephanie's lectures this morning. So this is an example of a simulation of outflow in our Milky Way galaxy. So it includes gas and supernova explosion and also radiative transfer. And so you see that people are trying to reproduce. So they are doing some simulation. They have some interstellar model. They implement some model equation, mostly so this MHD equation. And they let them evolve. And at the end, they evaluate the amount of mass which is rest at the disk and evaluate the star formation rate. Okay, so what could be the role of cosmic rays? So now how to implement first cosmic ray in such a trick. So you take again your MHD equation. Here it's one fluid. It's okay, an IDR. It's simplified for interstellar medium, as Stephanie just said this morning. And as I show you, so you have cosmic rays are active here in the total pressure term, combining gas and magnetic field. You have the cosmic ray pressure itself. And again, the gradient is a force. So adding a cosmic ray pressure gradient, you add some force on the gas, simply. And you can add some work on the energy. But in order to describe how the cosmic ray energy density evolves, you have to have an equation for evolution of the cosmic ray energy density. This can be this is not so easy to construct. Usually it is constructed from the Vlasov, some kinetic equation, Vlasov or Boltzmann, and you take some moments, and you can construct as for the fluid equation for cosmic rays for the gas density, or you can go to the 2 moments. Also have an equation for the flux of cosmic rays. This is a very active field of research. You have a series of processes which are important to evaluate the amount of cosmic ray energy density you have in your interstellar medium, which is on the left-hand side. So basically, you have the transport here, the diffusion. Here you have the work done by the cosmic ray pressure, and you have a series of terms you have to include in. So this is kind of complementary physics you have to rely on in order to properly calculate this energy density into cosmic rays. And this is not easy. So for the flux, usually you have this is in the flux, the diffusion coefficient of cosmic rays is entering. So you can apply all the model I showed you before, and you plug this model into this tensor, or let's say, to simplify, the parallel diffusion coefficient in 1D to calculate the cosmic ray flux. Then you have a series of effects which are associated to the fact that cosmic ray can stream, can move at a speed which is different from the gas. So we will induce some heating of the gas. And so loss for cosmic rays. You have a transfer energy between cosmic ray and gas. And so this is a gas heating term. So you have some source of cosmic rays through shock acceleration. I presented you before. So this is a source term. And also cosmic rays can have some radiative losses. So at high energy, for electrons, it is synchrotron inverse Compton. For proton, it's pion production. But at low energy, you enter into the ionization or Coulomb losses, depending on the level of ionization of your plasma. Okay, so, and then you have to solve this equation, and this is like some kind of trick. It's a very small, but just to show you that the difference between having no cosmic rays and with cosmic rays about the solution of gas of wind. And so you see clearly a difference, right? By eyes, you can see. And you see that basically adding cosmic rays produce faster winds and denser. That means that likely cosmic rays will participate to lower the star formation rate. Okay. And this is actually what you can see on this picture. It's not easy. So the case with no cosmic ray is gray here. And then adding cosmic ray physics will systematically produce lower star formation rate. Okay, so you see you have a kind of dispersion, which is dependent strongly on what type of diffusion coefficient you can take. Of course, because if you take a very large diffusion coefficient, you will basically decouple gas and cosmic rays. So you will get closer to this one. But if you have a very small one or a zero, you are a strong coupling between the gas and cosmic rays. And so the cosmic rays will be, the cosmic ray pressure will participate to counterbalance, let's say, the gravitational collapse even. So you can, so you have a, systematically, you find the lower star formation rate at for smaller diffusion coefficient. This is a kind of, there have been plenty of groups doing this kind of simulation recently, and this is more or less the takeaway message, factor 2. Okay. It's not huge, but it's more precise than without any cosmic rays, of course. An interesting aspect is actually there is a lot of debate because, as I told you, gamma rays are interesting because they once you have a good model for the gas in your galaxy, and then you can test your model for cosmic rays. You input it, and this model of cosmic ray depends on the diffusion process you implemented. This is what actually people are doing. So gas luminosity is a convolution of gas density and cosmic ray energy density and the gamma ray emissivity. So looking at the gamma ray emission from our galaxy or other galaxies, there is in fact a correlation obtained by especially the Fermi satellite, which is sensitive between 100 MeV and a few tenths of GeV, which have observed many other galaxies and report the luminosity in between 0.1 and 100 GeV as function of the star formation rate. And there is a correlation, or a kind of correlation, on our Milky Way is here, about, yeah. So I don't know, yeah, it should be more or less around, let's say, like M31. Here you have the starburst object. M82 I showed you before is here, and GC253 also is here. And one extreme object is ultra-luminous infrared galaxy, R220, which shows a huge star formation rate, about 100 solar mass per year. And you have higher gamma rays. And you need to explain this correlation using this, this model. Once you know the cosmic ray distribution, you are able to test it. And here is more or less all the different groups. So you have the different references in that paper, which has compared this. And you see that you have a huge dispersion from the expected gamma rays predicted by the different groups. And here, there is some discrepancy. If there are some agreements about, let's say, the order of magnitude of reduction of star formation rate by cosmic rays, the exact, let's say, cosmic ray physics you have in each galaxy is you have a huge dispersion here. And this is likely connected with the gas model, which are used in the different simulations, which can produce you very, so you have a huge scattering because of this term. But you have some uncertainties also on the diffusion process. I just wanted to mention that the diffusion, let's say, the way the diffusion coefficient is implemented in the cosmic ray model, this one, is usually very simple. People are using usually one value. If they are considering one population of cosmic ray, it's possible to have more complex model, like different population of cosmic rays, like that doing Philippe Girichidis. But let's take one. And usually what is done is that they implement one diffusion coefficient, typically 10 to the 28 centimeters square per second. And they look what does happen. And this is one case here for isotropic diffusion coefficient. You have one solution. But as I show you that the cosmic ray transport is much more complex than this. First, you can have anisotropic diffusion coefficient. So you have diffusion coefficient different along and perpendicular to the magnetic field first. And then cosmic ray can generate their own turbulence. This is not included in this simulation yet, because in fact, the scale in question where the coefficient diffusion may be modified by self-generated turbulent cosmic rays is at subgrid scale. So you have to do some subgrid physics. It's not an easy task. It is possible if you, let's say, follow the cosmic ray gradient in your grid, you are able to do this. And so at some position where the cosmic ray gradient is larger, some values, you can move to another diffusion model connected with streaming instability, for instance. This is what is starting to be done by, there is a publication, I cannot find it again, of course, by Semenov recently. What they did, they use an average diffusion coefficient for the galaxy, and around sources, they reduce it considerably and look for the star formation rate, the effect of a star formation rate. And there is some huge effect. So I told you about large scale. Now I'm moving to small or intermediate scale, and then coming to the question about ionization. Okay, so there is this trend. This is the ionization rate of H2 molecule per second as function of the density column. So there are plenty of observation, you see, from diffuse cloud to coarse. And the global trend, let's say, is that it is decreasing with increasing column density. So these are all effects combined. I mean, radiation, I don't know, basically, yes, radiation and cosmic rays. You can try to take, this is a typical value of the cosmic ray ionization rate taken from a local medium from a paper which is back to 68 by Spitzer Tomasco. And this 10 to the minus 17, in fact, it's a limit. It's not really a measurement. So you see that you have a lot of ionization rate which is above this line. How to explain it? So to connected to your remark is that if you immediately plug the model we are extracted from the Voyager data, I think you are here. Okay. So if you take the cosmic ray spectrum at low energy, which are important for ionization, we have from the Voyager data measurements, you are unable to explain this correlation, this trend or correlation, I mean. And so you have to have invoke either low energy cosmic ray in our galaxy is very intermittent. So we are in peculiar place in the galaxy, and then it may vary a lot. That's possible. Or you have associated with this object in situ source of non-thermal particles, which can help to have let's say, spectra which are able to explain this correlation. So this is the object of the rest of my lecture. But this is not the only point, is that if you are looking for now a star-forming region, these are more or less a region which are where you have not a lot of stellar activity. But if you look for ionization rate in a stellar active region, here you end up with ionization rates which are, you see, about several order of magnitude above that, up to 10 to the minus 12 in the center of our galaxy. So this is challenging to explain. I mean, so maybe cosmic rays can help do that. And the way is not clear now, and it's still an open question. And if you are interested to do some postdoc or PhD thesis on that, I think there is a lot of material. So you can have, as I told you, in situ sources of cosmic rays at intermediate molecular cloud size, which can be associated to H2 regions, molecular cloud, or supernova remnant. There have been some observation of, let's say, the supernova remnant W28. We effectively see enhanced ionization rate, about 10 to the minus 14 per second, around the supernova remnant. So likely associated with the injection of low energy cosmic rays by the supernova remnant itself. They can accelerate in source and then be transported in the interstellar medium. So this strongly depends on the diffusion coefficient, now not at GeV, but at MEV, which is even less known now in the model. I would like also to have a special mention on young stars, because these objects are numerous. They have some jets. They have a substantial jets duty cycle during their lifetime. And some of them have been observed showing non-thermal particle radiation. So they are accelerating particles. So they can deposit some cosmic rays into at small scale into the interstellar medium. Sorry. Okay, just to show you that the cosmic ray spectrum can be, at low energy, can be very intermittent. Here is the same model I show you for supernova remnant escape at 10 GeV, remember, for some phase, warm interstellar medium or warm neutral medium, but now at MEV energy. The people, these guys have done the same, but at low energy. So they solve a couple of equations of cosmic ray pressure and wave pressure, and they calculate the cosmic ray spectrum. They escaping as function of time, and to see that you can have substantial confinement, so the diffusion coefficient with respect to what we should have from the B over C measurement here, which is in the solid line, is substantially reduced for some time, up to 1 million years around a source. So this points toward that low energy cosmic ray distribution is likely very intermittent in our galaxy. Here I have a series of sources of non-thermal particles you can have in the interstellar medium. Here's an example of H2 region. So H2 region have some shocks, which are not fast, quite fast, but in fact, you don't need to have a high energy particle. You just need to accelerate non-thermal particle up to, let's say, a few hundred MeV to have an impact over ionization. Is an example of the galactic center. It's a Sagittarius B2 molecular cloud at the galactic center at radio by the VLA, and which shows in different parts very non-thermal negative index, which is synchrotron radiation. So we have a model for shock acceleration. So you plug the shock acceleration model, and to try to explain this data. And so we more or less succeed to fit the different part with reasonably energetic, with reasonable energetics. We don't need to accelerate 50% of the shock kinetic energy into cosmic rays. You just use about 10%, and we succeed to reproduce this data well. So H2 regions may be some source of cosmic rays. Another possibility is that in molecular clouds directly, there is turbulence, and this was presented this morning. Molecular clouds are supersonic, so you have shocks. And if the magnetic field in the Alfvénic Mach number is not much smaller than 1, in fact, the magnetic field is dynamically not important. It is let's say, a shield with the gas motion. Okay. And so that means that at small scale, because you have turbulence, you can have a phenomenon which is the reconfiguration of the magnetic field, which is magnetic reconnection. Right? And so you have a different orientation of the magnetic field line, which will recombine, transfer magnetic energy into heat and non-thermal particles. And this is a model which has, I told you, cosine Stephanie with brown gauges, which is a model for particle acceleration directly at molecular clouds to the reconnection process. So the acceleration process itself is like a shock. It's a Fermi. So the particles are crossing back and forth the reconnection region, and they gain energy each time they cross. And they have made some try to explain the range of ionization rate you can have depending on the diffusion law of the cosmic rays in this medium, and they find some solution, in fact, which can fit in that energy ionization rate domain. So this is another possibility. Let me finish with young stars. So this is a kind of, I would like to talk about this because I work on that. So I'm happy to try to share this with you. In fact, so what we have done with Marco Padovani is to investigate particle acceleration, especially at jets. So here is a picture of a sketch. So you have the accretion disk, the star, and then a jet. And we have tried to isolate where the site where you can accelerate particles or find by shocks. So you have different places where you can have shocks. So it's not working anymore. Not problem. So you have accretion shock. So matter is accreted on the star with a shock, and you can have shocks along the jet. As I show you by the VLA observation, you can have a recollimation shock along, or the termination shock when the jet is impacting the interstellar medium. These are all sites of potential particle acceleration. And so what we have done with Marco is to calculate, especially the particle acceleration can be accelerated in a internal shock and the termination shock for some object, for instance, for GISM2 object. And we calculate the synchrotron emission at the hotspot of GISM2 and try to fit the VLA and GMRT data. So we were able to do that with reasonable, let's say, values of the cosmic ray energetics and magnetic field. The interesting aspect also is that you can, as you can produce a lot of particle at, let's say, GeV or a bit less, the maximum energy at this shock is about a few tenths of GeV. It's not spectacular, let's say, but it is enough to have a population of particles which are able to ionize your environment. And we were able to explain, for instance, the ionization rate deduced in the OMC2, OMC3 and 4 FIR4 object, which is an intermediate mass object, which shows a high ionization. Oh, okay. Can do some baseball. So I make a try to evaluate the kind of cosmic ray luminosity you can have in that jet. It's a very, let's say, -1 order of calculation, even not 0 order. Yes, that's fine. You take the jet's luminosity. I'm not tall enough, but okay, jet luminosity here. You take the jet ejection rate as a fraction of the accretion rate. Okay, you can always do that. You can take the jet velocity as a fraction of the Keplerian velocity on your disk, because the jets are launched from the disk. Okay, you have two factors which can be evaluated either using observation or theoretical works, which typically fall in that order for solar-like objects, mass. And then this is easy to calculate a typical luminosity of 10 to the 31 erg per second in cosmic rays. If you take 10% of efficiency, converting your shock kinetic energy into particles. So this is not a lot. No, okay, you agree? But you have a lot of source. So, I mean, combining all this luminosity can possibly, we did not evaluate it, contribute to a kind of injection of non-thermal component, which again can be important for ionization stuff at small scale. It is also interesting at higher energy because massive young stellar objects also have jets. And what is interesting in these objects is that the jet speed is larger. Can get up to 1,000 kilometers per second for HH 8081. And if you increase the shock speed here, you will decrease the acceleration time scale for the particle. So at this, typically you can get higher energies in this object because the shock is faster, and then you can reach not a few GeV, but you can reach eventually TeV. And this is interesting because then it can be constrained from gamma ray observation. Here we computed the multi-wavelength radiation from several of these objects. And here is the Fermi upper limit after 10 years. And in some objects, so we can start to constrain the model. And what we would like eventually to see if it can increase up to TeV, which it can be probed by the next generation of Cherenkov telescope mentioned previously, especially the Cherenkov telescope array, which will be implemented in the Canary Islands and Chile, which will be operational fully in 2 or 3 years. Who knows? Just to finish about the very small scale now, about around the star, the accretion disk at, let's say, a few AU. We have started at Montpellier a PhD work on that because, in fact, we know that T2 stars are stars which are magnetically active and much more active than the sun. Actually, they produce proton fluence from their flare about 5 orders of magnitude above what we have from the sun, actually. And the young sun is much more active than our sun now. So this magnetic activity can have some impact over the accretion process close to the star. And this is known for long that you can launch jets from the disk, from the stellar component also. And in order to launch this, you have to convert somehow the magnetic energy stored into gas motion, where it can be greatly helped through the magnetic reconnection process. Okay. As I told you, magnetic reconnection convert magnetic energy into heat, which is important to, let's say, deposit some energy at the base of your flow to help, yes, help for the ejection, and especially the Blanford and Payne process needs to have some pressure imparted on the gas at the base to help to eject the material. But on top of that, they can produce non-thermal particle. Non-thermal particle will propagate along the magnetic field line, and eventually they can propagate also in the disk, accretion disk, and penetrate at high column density in the disk. And this is important because the ionization rate, the ionization fraction in the disk, in fact, controls the magnetorotational instability. So you can have close to the star or eventually a bit larger distance, but likely associated with the activity of the star, some feedback from in situ accelerated particle into the accretion disk, which can help some kind of with episodic activity, the accretion process towards the star. And eventually, even a bit larger distance, because it's not forbidden to take this kind of model you have in molecular clouds. If you have some amount of minimum amount of turbulence, you will have some reconnection. And in fact, if you have minimum amount of turbulence, let's say at up to 10 AU, a bit beyond, it's maybe more constrained by observation. So you have a rather low level of turbulence, but at least you have a minimum level of turbulence. You can have also a production of non-thermal particle. And this is what there is a different work that have been done recently on that, trying to gather the different sources of non-thermal, let's say, yes, ionization source in the accretion disk. Here it's from a model, a chemistry model of a disk done by a code which is ProDemo. And people have Christian Raab here and collaborators have included so X-rays from the star itself, external cosmic rays, which are partly shielded by the stellar wind, and in situ source of cosmic ray associated with the stellar activity. And depending on the model, you end up with a different source of ionization. Here, it's you have a different color or different source of ionization, X-ray, stellar particle, cosmic ray. And then from that, once you know this, you can calculate the main ion species component and try to make some observational constraint. Would be ideal to calculate the ionization rate in the disk. And again, it's very important in the control of the accretion process. Well, I am in time. It's a bit of surprise. No, but I have skipped some slides. Okay, you can read it. So my takeaway message is, of course, let's say, including cosmic rays in ISM dynamics at all scale is a new stuff. Okay, and so there are some results which are starting to be to make some consensus that you have indeed some regulation of star formation via winds at large scale, but let's say a factor of 2, as I told you, which is a bit sensitive on the cosmic ray transport model, which can be constrained by the gamma ray observation. Then at small and intermediate scales, the ionization of H2 at large column density is really connected with the cosmic ray physics, because it's very difficult for, let's say, primary radiation to penetrate at such high column density. You can have secondary radiation, let's say, because cosmic rays propagating in molecular clouds can produce UV radiation, which itself can produce some further ionization, but this is connected with cosmic rays. And then in order to explain the huge enhancement of ionization in H2, especially in active regions, you need to have some in situ source of cosmic rays, or to have specific zones connected with the stellar activity where you have some modified transport of the cosmic rays. So cosmic rays are more confined, longer around their source for a longer time. But this is still an open question. There is a lot of aspects I did not treat. I put some old topics here. As it is a new subject, it's widely open, and it's moving in whole directions. It's difficult to follow. Just want to mention that this eternal EC team, I organized 2 weeks ago or 3 weeks ago a meeting where there was a guy, the PI of this eternal EC meeting, which gave a talk about the impact of energetic particle over planetary atmosphere. And it was really incredible. The amount of knowledge you need to constrain this effect. You need to go from cosmic ray plasma physics to chemistry. You need a very wide knowledge. And this is why this team is quite large. But they reached some very nice results. So you see that from the larger scales of the galaxy to planetary scales, let's say non-thermal energetic particles are they word to say, and maybe they are worthwhile at some stage to be included in ISM studies. Thank you for your attention. Sorry for this stuff. I think I have some magnetic effect, or I don't know. Cosmic.
Thank you.
Thank you.
So we have some time for questions now.
Oh, yes.
Students first, of course.
No,
Thank you again. I was wondering, in the picture you showed about the shocks in the sheds of the stars, if you consider a reverse shock, and if it could contribute to something.
So basically, we consider the reverse shock. In fact, the shock which is more likely adiabatic, in order to accelerate particle. Acceleration of particle in radiative shocks is thought to be not efficient because, in fact, in the injection process, so you extract few particles from the shock thermal plasma and you put them at non-thermal, let's say, relativistic speed. If the shock is radiative, you have likely more denser medium, and then at these injection energies, I have to get right about losses, because you have strong ionization or Coulomb losses. And this is one especially impact you expect in these radiative shocks. And especially also if the radiative shocks are slow, as it is the case for all supernova remnants, let's say sinus loop, the shock speed is about 100 kilometers per second or less. Then you don't have from the shock plasma, the radiation is not strong and at the right frequency to ionize the upstream medium. So the upstream medium is partially ionized. So neutrals are bad for waves which can scatter particles back and forth the shocks. They will damp the waves. So they are bad candidates to accelerate particle. Saying that, we have detected novae at gamma rays, and the shock in the novae are very likely and in the radiative regime. And the difference here in the radiative nova in the novae is that the shock has a speed of 3,000 kilometers per second. They are much faster. And this is likely another effect. So behind the shock, you have a radiation at X-rays, which can ionize. Also, likely the acceleration timescale can be much smaller. And then particle can get right about the losses, and they can get accelerated. So this is not completely excluded that radiative shocks can accelerate particles, but it's likely more difficult, let's say.
Thank you.
Other questions?
Yeah, I was intrigued by your mention of dust on the last slide. Could you say a little bit about it?
There's an interesting work. It's nice. I have backup slide on that. It's very new work. So the work I understand about dust. I'm not well aware about desorption stuff, etc. Sorry for that. What I'm more aware about is that how dust can impact cosmic ray transport. And this is new stuff by a very nice paper by Jonathan Square, which shows that, in fact, dust can, in fact, either enhance the cosmic ray transport, that is, produce less confinement, or produce more confinement, depending on basically the drift speed of the dust, depending if it's smaller or larger than the advance speed. You can have very different effects, and this is because they have an impact over the Alphen waves. They can either damp the Alphen waves. If they damp the Alphen waves, cosmic wave can flow more ballistically, and they are less confined. And depending on the type of regime you have, they can impact substantially over the cosmic ray transport process. So in turn, if you want to implement a good cosmic ray model in your ISM studies, you may have to account for this effect. But this is more or less the only answer I can give you, because of the aspect of let's say charging, discharging, I'm not a specialist at all. So again, I would suggest for next year to have invite some good people on that good lecture.
Hi. Yeah, many thanks. This was great. I wanted to follow up on the previous question, because I was wondering about cosmic ray acceleration in stellar winds, and how important that is, maybe with respect to supernovae. I mean, are they negligible or not? And then maybe because also we don't really know how well the wind is mixing with the surrounding ionized gas, whether this would be a possibility, whether one could constrain this by looking at gamma rays, for example, because you were mentioning that the acceleration in radiative shocks depends on yeah, the type of radiation you get and so on. Thank you.
Yes. We know that winds are participating to the cosmic ray spectrum because there is some what's called anomalous effect in the cosmic ray distribution, especially to what regards the neon 22 abundance. The neon 22 abundance is tells us that you have at least a fraction of cosmic ray which are accelerated in a Wolf-Rayet stellar winds. I don't remember exactly the amount, but it's of the order at least 10 to 20%. Yeah, so we know that stellar winds are contributing somehow to the cosmic ray. Now you can have a supernova shock moving into the Wolf-Rayet star, but as also massive stars are in a cluster, they are likely also possibly to inject let's say cosmic rays as at stages earlier than any supernova explosion. But we know that massive stars are contributing to the cosmic ray spectrum. That's for sure. Yeah.
Thanks for the talk. I have two questions. One is, how would you characterize the effect of cosmic rays on a complex cloud? So, for example, if the cloud has clumps, or if the cloud is, generally obscured. I understood that low energy cosmic rays would still go deep into the cloud and cause some changes in the H2.
Yeah.
But
this is this picture basically. You are here at the higher end of. So they can ionize deeply, and also, as I told, while producing ionization, they can also excite the different species here, and especially you can have a production of secondary radiation, UV photons, and secondary electron and positrons also. And especially at very high Coulomb densities, above 10 to the 26 per centimeter square. In fact, it is not the primary cosmic rays which are important. These are the secondary, in fact, species which are mostly taking care about ionization. So UV radiation, but also secondary electron-positron produced by the charged pion decay, not the natural one, but charged pion decay in electron-positrons, which are, these are the results shown by, there's some paper by Alexei Ivlev and Macro Padovani on that, which clearly show that at high Coulomb density, you have not an exponential cutoff of the flux of the particle as was thought before. But if you calculate properly the propagation of the particle, which in that case is a diffusion through the collision now, you have a kind of tail of particle which is associated with secondary electron positrons, which are taking care of the ionization at very high Coulomb density. This is a very, let's say, a firm result, robust result.
And a connected question would be, if we then look at the diffuse regions, would you say that the emission of a cooling line, for example, C+ would be connected to cosmic rays that might not be emanating from the cloud itself?
This is a question I don't know. I cannot answer you. I have not, honestly, I cannot answer.
And the last thing was, you'd mentioned GMRT data at a slide near 70, I think. Can you just repeat?
Yeah, so we use a GMRT data. I don't know if I have a plot here for. I was speaking about GMRT data for this type of stuff because GMRT has observed digital, well, a kind of archetype of T2 star, let's say. And what they found on the hotspot, they have found non-thermal. So if you combine VLA and GMRT, you have a nice non-thermal slope. And so you are clear acceleration of non-thermal electrons there, which are radiating at synchronous. So the amount of electron you need to explain this can help also to ionize locally the medium. That's I don't know if I answered to your question.
Okay, I think it's about time to
Yes.
finish. So thank you again for
Thank you.
reading lecture.